Our next speaker is Ubirajara van Kolck. He's Director of Research at France's National Center for Scientific Research and Professor of Physics at the University of Arizona. He received his PhD in 1993 from the University of Texas at Austin under the supervision of Steven Weinberg. He held postdoctoral appointments at the University of Washington and at Caltech. He holds visiting positions at the University of Washington and at Paulista in Sao Paulo. He has been a Riken BNL Research Fellow, a U.S. Department of Energy Outstanding Junior Investigator, and an Alfred P. Sloan Research Fellow. He has served as chair of the APS Group on Few Body Physics and as member of various advisory boards, for example, at the Institute for Nuclear Theory in Seattle and the European Center for Theoretical Studies in Nuclear Physics and Related Areas in Trento. He was elected Fellow of the American Physical Society in 2004, and he received the Paul Engem Prize at the French Society of Physics in 2015. He's given more than 100 invited talks in international conferences and published over 90 scientific articles. His interests center on effective field theories and the emergence of nuclear physics from the Standard Model and its extensions. So today he'll talk to us about nuclei in the Standard Model and beyond.
Thank you. I'm going to talk about nuclear physics and within the Standard Model, though. And I'm afraid that some of my teen idols might share this opinion about the physics of nucleons that was expressed a long time ago by Goldberger, which was mentioned yesterday. Not a very flattering statement that ends with the opinion that it looks like many people don't even know what the problem is. My goal today is to try to convince you that at least we have an idea what the problem is after those 70 years. I think the question we want to ask nowadays, and it was asked already in Professor Bjorken's talk yesterday, is can we understand the emergence of nuclei within the Standard Model? I think that has at least two advantages. One is that it might teach us about non-perturbative physics in perhaps the simplest context that we can think of, one that's non-relativistic. And as I'm going to mention later on, we see in this theory fixed points, limit cycles, and other interesting features of the renormalization group. And a more practical advantage is that if we can insert nuclear physics within the Standard Model, then we can look for deviations from the Standard Model. And two examples are the most famous, perhaps, neutrinoless double beta decay, but also other things like nuclear electric dipole moments. I'm going to try to show that the method to answer this question here is based on nuclear effect field theories. Nuclear effect field theories, we have been working on those for 25 years now, so it's a lot of progress. I cannot describe everything. It has become now the standard theory for most calculations in nuclear physics, so this was a great success. And the reason is that it's an implementation of the quantum field theory paradigm in nuclear physics, and it solves, I think, or at least most of the renormalization problems of the 1950s, which were sort of responsible, I think, for the separation between nuclear and particle physics. So the outline of my talk, I'm going to say a few words about effect field theory, and then I'm going to spend most time talking about the two most important effect field theories that we have developed in nuclear physics, one called Cairo effect field theory, the other one Pine-Less effect field theory. If I have time, I'm going to give a couple of examples of applications to beyond the Standard Model physics and then conclude. So from my perspective, I'm young, well, not really anymore, but compared to the Standard Model, I'm young, I guess. And I think the most important feature of the Standard Model for me is what it's not. It's not a fundamental theory, as was emphasized in a couple of talks before, but an effect field theory. Now, I don't know exactly what was in the minds of the creators of the idea of effect field theory. The main one is present here, Steve Weinberg. But I imagine that it must have been this combination of two striking features, the successes of the Standard Model and the gauge coupling unification. One way to understand this is to say that the theory is really the dimension 4 operators that sometimes is called the standard model plus higher dimensional operators. And this was captured in a very clean way by a pseudo theorem by Steve that says essentially that if you start with the most general Lagrangian with certain symmetries, you get the most general S matrix theory with the same symmetries. So we are not going to necessarily truncate at the level of the leading operators, but you're going to include all of the interactions consistent with the symmetries. So my version of effect field theory is this. We are always, in physics, we always probe a limited regime of energies or momenta, which I'm going to call M high. So we are usually interested in a situation where we want to study processes at certain external momenta that are comparable to a low energy scale, which I'm going to call M low. And what we want is to write the S matrix in a controlled expansion in powers of Q, the external momenta divided by the mass scale of the underlying theory, M high. So this theory is hopefully we can write the S matrix that way, so it will have an expansion parameter which is not a coupling constant. And then at each term, at each order of this expansion, we are going to have some terms that are non-analytic in the momenta, and we can get those from loops. Or in some cases where the physics is non-perturbative, we might resum the loops in the Schrödinger equation or the Lippmann-Schwinger equation or what have you. Now, the theory will have an infinite number of parameters if I go to infinitely higher order, but up to a finite order, it will have a finite number of parameters which are in the nuclear physics literature called low energy constants, in particle physics frequently called Wilson coefficients. And the reason why we want this is because then we can truncate, and then we have an error that's going to be a controlled error that's small. Now, this being quantum field theory, we're making an expansion around the point limit, so we need to introduce a regulator. Here I'm going to be thinking mostly about a momentum regulator. Dim reg is not the most useful regularization technique in these problems. And so we want to introduce this ad hoc regulation procedure, but this is not physics, so we want to, a very important constraint is renormalization group invariance, that our S matrix does not depend on the regulator procedure, and once we truncate that, it depends very weakly on the regulator, and therefore, if we take the regulator parameter to be very large, we can reduce the breaking of renormalization group invariance as much as we can. So now applying this to QCD, my QCD is going to be the QCD light of yesterday. So just two quark flavors for simplicity, and we've discussed already a bit in this meeting how beautiful this theory is. For me, the most important, I'm going to need essentially just two aspects of QCD explicitly. One is, as we know, that the theory becomes non-perturbative at low energies, so there is a scale that emerges associated with non-perturbative physics, and that's a number of order 1 GeVs associated with the masses of the hadrons, or 4 pi times the pi decay constant, and so on. The second feature that I need is the fact that, well, sorry that this graph looks so, this plot looks so ugly in PowerPoint, where I can do this better, but if you neglect the quark masses, we have the phenomenon of spontaneous breaking of chiral symmetry. There is a set of minima that are degenerated. Those we can associate with the pions, and once we include the quark masses, then there is the potential changes a little bit to the green line here, and the pions have a small mass corresponding to oscillations around the circle, and that introduces another scale, then factor the number of the pion mass, which is about 140 MeV. Another scale that will appear in the following is the pion decay constant, which is essentially the radius of this chiral circle, which should be something like MQCD divided by 4 pi, which is also a number of order 100 MeV. So these are the scales that we have to contend with, numbers of order 100 and 140 MeV versus 1 GeV. So the picture that so in a plane where I put the momentum here in the pion mass, perturbative QCD is there in the sky. Below that, the physics that we want to describe of real nuclei, we can estimate the typical momentum for a bound state according to its binding energy per particle and the nucleon mass. And it's going to be a number typically of order 100, 200 MeV. So we are in this non-perturbative regime. And moreover, one that nucleons are non-relativistic. So we are going to try to design then effect field theories that are non-relativistic for nucleons. And the most famous one is perhaps the most powerful in some sense, is chiral effect field theory, is when we include pions as explicit degrees of freedom. And as I'm going to show, in general, pions are non-perturbative, but there's a region where we can do perturbation theory in the pions. This effect field theory has also an expansion in powers of the pion mass. So if I go away from the physics point, at some point it breaks down. So roughly to have a border of validity like this, and in this plane of momenta and pion mass, that's where this theory lives. And I'm going to start with that. Eventually, we want to go from QCD directly to the physics of nuclei. I think in practice, we want always to match with chiral effect field theory. That is not what we can do at the moment yet, because calculations in lattice QCD, for example, have not gotten to this low pion mass, not for nuclei yet. But I'm going to have a few things to say about matching with lattice QCD later on. This chiral effect field theory is then a theory for momenta of order of the pion mass, much smaller than MQCD. So I'm going to follow the usual rules to construct an effect field theory. I'm going to include the low energy degrees of freedom. Basically, nucleons and pions are some other sophistications that we can introduce, but with the symmetries of QCD, besides the ones to use that we use in the explicit construction of the QCD with quarks and gluons, also this spontaneous breaking of chiral symmetry, and the Lagrangian has an infinite number of terms, pion terms and nucleon kinetic terms, pion-nucleon interactions. We had a lot of discussion about those in Adler's talk yesterday. And then interactions that involve purely nucleons at small distances. And then I didn't write here all the other possible combinations of spin and isospin and so on. This theory is an expansion in Q over MQCD, but it's combined expansion in relativistic effects, what you could say is a multipolar expansion, and also an expansion in pion loops, because frequently this combination comes about when you consider pion loops for pi f pi. So this theory has a long history in the sector of pions and nucleons. It's what's called nowadays chiral perturbation theory. What I want to discuss is the extension to the sector with two or more nucleons. And the main feature here is that the theory is non-perturbative as opposed to this regime here. And the reason for this non-perturbativeness was pointed out by Weinberg in 1990. If you look at diagrams, typical diagrams in chiral perturbation theory, and you look at an intermediate state, the difference in energy is a number of order of the pion mass, while if you have two or more heavy particles, in this case nucleons, you can get enhancements due to the kinetic energy of the nucleons. So you get this large scale in the numerator that doesn't appear in chiral perturbation theory. So one way to deal with this problem is to define a thing called the potential. So the potential is defined as these irreducible diagrams, and so you have an infinite number of diagrams contributing to the 2 nucleon potential, to the 3 nucleon potential, and so on, where nucleons exchange pions or have their contact just naively, so the first applications were based on naive dimensional analysis. Naive dimensional analysis was conceived as a way to estimate the size of the short-range interactions based on chiral perturbation theory, based on a perturbative analysis. And so if you assume that, you see that the two nucleon potential will have a leading order term, which is just one pion exchange and contact interactions. And it's given by a scale that was introduced later by Mark Wise, who is here, and collaborators, which they called M and N. And in naive dimensional analysis is essentially F pi. So this is important because if you look at the sum of the series here with this leading order potential, you have a common factor given by this M and N, and then the loops contribute a factor of Mn q over 4 pi. The Mn is Weinberg's infrared enhancement, and then there's an extra 4 pi here. And you see that schematically this series is one that will have a pole at q over M and N. That could be a bound state, so it could be a nuclear bound state, could be a resonance, but in the cases of most interest bound states, and this scale comes out to be roughly of the right order of magnitude. So this is not always appreciated, that because of spontaneous chiral symmetry breaking, because of the existence of this parameter F pi here, nuclear scales arise naturally in the standard model. And then Brian Lin, for example, and collaborators have shown how some standard nuclear models contain the scale F pi once you study the size of contact interactions according to naive dimensional analysis. So this can be pursued at a higher order, so higher derivatives, more nucleon interactions, again using naive dimensional analysis, can push this potential to very high order. Most of the calculations done nowadays are with chiral potentials, which means a truncation of this expansion, and then an exact solution of the many-body Schrödinger equation. So these are called ab initio methods, and this has really taken off in nuclear physics, so there are lots of calculations of this type. This is only one of them. These are calculations of the binding energies of several nuclei here. Here is the efficiency in the charge radius. And all these points are different chiral potentials, different orders, different strategies for fitting parameters. And you see that phenomenologically, at least, it works pretty well. There is a fly in the ointment, though, and that was pointed out again by Mark and collaborators already in '96, that these calculations lack renormalization group invariance, unfortunately. They all depend on the choice of the regulator, and this is a big drawback. Mark also suggested a solution to this problem, which was to treat the pions in perturbation theory, and to treat the subleading potentials not exactly, but also in perturbation theory. And this works well, but only for momenta smaller than F pi or so. We've been able to adapt this solution to non-perturbative pions at the cost of realizing that the running of some of the counter terms, some of the low energy constants, is not fixed by MQCD, but they are enhanced by the pion exchange. They are driven by the pion exchange. But you still have to treat the subleading potentials in perturbation theory. So this is a very active topic in nuclear physics. I'm not going to go to describe any more of the results, except one, which might be of some interest to this audience, which is the fine-tuning that we have in nuclear physics. So this is a somewhat speculative mechanism at this point, because we don't really have lattice data at unphysical pion masses that close to physical. But one striking feature of the two-nucleon system is that the scattering amplitude at zero energy, the scattering lengths, are very large in the scale set by these pion parameters. And chiral EFT provides a possible mechanism for what this is. So if we vary the in these calculations, if we vary the pi in mass, for example, calculation for the scattering length in the 3s1 channel, the channel of the deuteron, we could have a situation like this, that the amplitude has a pole very close to the physical pi in mass. Why this critical pi in mass is close to the physical pi in mass is a mystery. That would be the critical pi in mass where the deuteron goes unbound. Whatever the explanation for this phenomena, that means that the theory is contaminated by a fine-tuned parameter, which you could say is a difference in mass between the physical pi in mass and the critical pi in mass. And that affects a lot of the nuclear observables that we have to deal with. The mechanism is a bit similar to what happens in atomic systems in what's called the Feshbach resonance, when you can vary the effective scattering length in one channel by applying a magnetic field that affects the coupling of this open channel with a closed channel and can drive a bound state in the closed channel to threshold. In that case, we have the same phenomenon of a large scattering length. We can have the possibility of dial to the so-called unitarity limit, where the scattering length is infinite, which would be close to the physical pi mass in the nuclear case. So that leads us to possibility of trying to explore the physics at this smaller scale. And that has led to the introduction of the other effective field theory I want to talk about, which is called pineless EFT. And for some of you, this might sound uninteresting because you like pions, because it's QCD. But on the other hand, this theory has very, very nice features, which I will briefly describe. Among other features, one is that lattice calculations in nuclear physics at this point are restricted to very large pi masses. And if you want to make the connection with lattice QCD, then for now we need to work with this spineless EFT. Spineless EFT is pathetically simple, perhaps. It's for momenta smaller than the pi mass. So the only degrees of freedom of the theory are nucleons. So the effective Lagrangian is very simple. It's just contain kinetic terms for nucleons and then contact interactions for 2 nucleons, 3 nucleons, and more derivatives and so on. So this theory is so general that it can be applied with very small modifications to atomic physics. And this is just a reflection that if you're close to this unitarity limit, you have a high degree of universality in your theory. So let's see why this theory is interesting. In this case, I only have a leading order one single interaction parameter, and this is given by this fine-tuned scale. And again, if I played exactly the same game as before, I see that this fine-tuned scale in the two-body system gives rise to a smaller energy scale, and that accounts for the fact that the deuteron, for example, is bound by 2 MeV. In the other one, the other S-wave channel, the one that's not channel, the energy is even smaller. So this theory can capture the physics of the deuteron and physics of very low energy, and it has very interesting properties. If you write the equation, the renormalization group equation for the properly renormalized coupling constant, you see that it has 2 fixed points, one that is trivial and another one that's non-trivial and corresponds to unitarity. At unitarity, this parameter here is exactly 0. So we have a theory where there is no physical scale and therefore scale invariance at this order in the two-body system. More interesting is the three-body system. If I write the two-body amplitude at leading order with this orange line here, and if I do the power counting in the three-body system in a scattering, for example, of one particle in the bound state of the other two, will contain an infinite number of diagrams, which I can write in a Lippmann-Schwinger type equation. And if you solve this equation, you're going to find something very, very strange. That the amplitude at a large momentum, you can show that analytically has a dependence on the cutoff, which is the cosine of the log. And this is very weird, but it has dangerous consequences, because if I vary the cutoff a little bit, my amplitude at low energies changes a lot. So I'm not renormalizing the theory correctly. The way to renormalize the theory correctly is to realize that the three-body force is a leading order effect. And once you introduce a three-body force in a non-perturbative way, it actually renormalizes the two-body system, the three-body system, and introduces a new parameter, which I call here lambda star. So we have an example of dimensional transmutation here in a non-relativistic setting, where a parameter appeared in a scale-free, what you thought would be a scale-free theory. And the three-body force in some units actually has an oscillatory behavior with the cutoff. This is a reflection of a renormalization group limit cycle, and that was speculated by Wilson way back when, and when Wilson heard about these results, he got very excited. The most important feature is that the theory then has discrete scale invariance with only one parameter, and this has plenty of implications to the low energy physics. So if I do an expansion about the unitarity limit, an expansion in this parameter in addition to the effect field theory expansion, then the theory is determined at leading order by one parameter, so non-perturbative, and all the rest is perturbation theory. So we have an approximate geometric tower of states. So that's an effect field theory derivation of what's called the Efimov effect. And the ground states of all nuclei in leading order are going to be given by universal numbers times the binding energy of the three-body system. One example of calculation is for the alpha particle. So it's what's phenomenologically people have found what's called the Chion line with phenomenological potentials. If they plot the binding energy of the alpha particle in terms of the binding energy of the triton, they found a line. And we can reproduce this line, we can understand this line as being a consequence of the variation of this one parameter lambda star. Here at unitarity, and here is once we take account the breaking of we take into account the breaking of unitarity, and this is experiment. So already at leading order, you see the type of description that we get for triton and alpha particle. People have not pursued that particular EFT for more nucleons, but we have done a similar calculation for bosons at unitarity. That was with Monte Carlo calculations. For bosons, the same phenomenon happened. The three-body force is leading order because there is no Pauli principle to prevent the collapse. And these are calculations of the energy of the n-body system divided by the energy of the three-body system per particle. As a function of number of particles in the cluster, there are different cutoffs here. They converge to a certain line here, and what we see we see saturation in this system. So this is not a nuclear calculation, but it shows the elements that we know from nuclear physics in the semi-empirical mass formula. The fact that we have a volume energy and a surface energy. Of course, in the nuclear case, we also have to deal with Coulomb energy and asymmetry energy and other smaller effects. But that gives us hope that we might be able to explain this mechanism of saturation with nucleons in the future. At physical quark masses, then I cannot make this expansion around the unitarity. So I have three parameters in leading order, but we can match those three parameters to lattice QCD calculations. So there are lattice QCD calculations at physical pi masses. So I take here one from the NPL QCD collaboration and pi mass of 800 MeV. With our three parameters, we determine them by requiring that the binding energies of the dineutron, the deuteron, and the trinucleon system are correct, and then we post-dict alpha particle energy. It agrees very well with the determination directly from the lattice, and then we can extend this to heavier nuclei. So this shows how in the future we can do the same thing for Caro EFT. We can match lattice QCD into effect field theory, and then let the effect field theory for light nuclei, and then let the effect field theory make the predictions for nuclear physics. Incidentally, we see that this picture, even though the pi mass is pretty high, is qualitatively similar to what we see at physical pi masses. Just everything is more bound by a factor of about 5. There have been other effect field theories developed in nuclear physics, which I'm not going to mention. One is for systems called halo nuclei, where there is a tight core of nucleons. There is an effect field theory for deformed nuclei. This is for another talk. In the minutes that I have left, I'm going to very briefly sketch some of the uses we can do this in beyond the standard model physics. So there's one dimension 5 operator, as you all know, that breaks that violates lepton number, leads to neutrinoless double beta decay. There are many, as it was mentioned before today, many dimension 6 operators. I'm just going to mention those that violate time reversal and lead to a neutron electric dipole moment. So in neutrinoless double beta decay at low energies, you know, the mechanism is driven by a process like this, where the two neutrinos sort of annihilate in the middle. And what we've shown is that this type of diagram here is not renormalized properly. You need a counter term already at leading order, so you need one extra parameter than what exists in nuclear physics calculations. This parameter can be related to parameters that appear in the renormalization of electromagnetic effects, but to disentangle the two, one needs lattice. If I neglect that disentanglement, I just assume that the one parameter is equal to the is just the sum of the other two divided by 2. Then we can make an estimate, and we can see that the effect can be typically 60%. That's the case, for example, in the decay of beryllium-12, where we can do this from with ab initio methods. Nuclear electric dipole moments, we can also learn something about them. Now the dimension, there are T violation at dimension 4 and 6, 4 from the theta term, but the theta term is pretty small, so dimension 6 might be important. There's a number of them. Quark EDM, quark color EDM, quark EDM, the Weinberg operator, or gluon color EDM, if you want, it will. Genuine contact interactions, and then contact interactions that come from W exchange. And the point is that if you measure the neutron EDM, it would be a great discovery. You'll see a T violation, but any source could explain it. All these operators generate in the effect field theory operators with different chiral properties, so they generate different sorts of pion exchange, and that can lead to texture in a matrix of the EDMs for proton, deuteron, helium, and triton in units of the neutron EDM. And here's an example, so you can see if the deuteron EDM is large, it would suggest that it's the quark color EDM might be the source, and so on. Then there are specific relations that allow us to further disentangle these various operators. So that's an example where nuclear physics suggests that if people do perform storage ring measurements of charged particle EDMs, as it was suggested by some people, we could learn about the T-violating sources. So with that, let me conclude. Sorry for going a bit fast. The conclusion is very simple. I try to show that we are already at a stage where effect field theory allows us to connect the standard model in nuclear physics in a way that's systematic and controllable, and that we are in position to, in at least a few cases, use nuclei as laboratories for new physics. Thank you.